Safety procedures
to be adopted inside thermal power plants. All the trainees are requested to wear their personal protective equipment as per their working environment.
Dear trainee, during the course of your training, you may have to visit different locations, and it is important that you ensure your personal safety and that of your friends while you're inside the plant premises. In order to complete your training program successfully and safely, please follow the instructions. Do not walk barefooted anywhere inside the plant. All trainees should wear tight-fitting clothing with helmet and shoes. Female trainees should not leave their hair loose. Do not move anywhere inside the plant without authorized guidance. Never go near any running machinery. Do not support yourself on any pole, scaffold or any other elevated structure. Do not operate any push button or switch unknowingly. Do not engage in conversation by standing in stairs or passageways. Do not stand under any suspended load. Extreme care should be taken before approaching live equipment. Maintain safe distance from the live equipment. Do not touch high-temperature steam lines. Do not cross conveyor belts except at the crossover ladder. Never open any of the peepholes without proper safety goggles. Never indulge in any sort of adventurous activities inside the plant. Introduction. For 60 glorious years, NLC India Limited, formerly known as Neyveli Lignite Corporation, has been a forerunner among public sector undertakings in the energy sector, contributing to a lion's share of lignite production as a different share on the thermal power generation. The unique feature of NLC India Limited is its twin objective of mining and power generation, which it pursues with excellent record of performance. NLC India Limited is a Navaratna Government of India enterprise coming under the administered control of Ministry of Coal and a pioneer provider of India's energy security with a rich history. NLC India Limited operates 3 open-cast lignite mines of total capacity of 28.5 million tons per annum and 1 open-cast lignite mine of 2.1 million tons per annum capacity at Barsingsar, Rajasthan. NLC India Limited operates 4 thermal power stations of 2,990 megawatt capacity at Neyveli and 1 thermal power station at Barsingsar, Rajasthan with an installed capacity of 250 megawatts. 1 coal-based thermal power plant NTPL at Thoothukudi of 1000 megawatt capacity joint venture project of NLC India Limited, TANGETCO. Thermal Power Station 1. The 600 megawatt Neyveli Thermal Power Plant Station 1 is the mother of NLC India Limited thermal power plants. The first unit was synchronized in May 1962 and the last unit in September 1970. It consists of 6 units of 50 megawatt each and 3 units of 100 megawatt each. The power generated from Thermal Power Station 1 is fed to Tamil Nadu Generation and Distribution Corporation and Pondicherry Union Territory. Thermal Power Station 1 has been expanded with 2 units of 210 megawatts each using the lignite available from expanded Mine 1. The Unit 1 was synchronized in October 2002 and Unit 2 in July 2003. The power generated from this thermal power station is shared by the southern states. Thermal Power Station 2. The second thermal power station consists of 7 units of 210 megawatt each. The first 210 megawatt unit was synchronized in March 1986 and the last unit was synchronized in June 1993. The power generated from second thermal power station is shared by the southern states. Thermal Power Station 2 Expansion consists of 2 units of 250 megawatt capacity each. Unit 2 attained commercial operation in April 2015 and Unit 1 in July 2015. The circulating fluidized bed combustion technology has been adopted for 250 megawatt capacity units for the first time in India. The NLC Tamil Nadu Power Limited consists of 2 into 500 megawatt coal-based thermal power project at Tuticorin in Tamil Nadu is a joint venture company with Tangetco. The Unit 1 attained commercial operation in June 2015 and Unit 2 in August 2015. Mahanadi Coalfields Limited supplies 3.0 million tons per annum of coal and the shortfall is met with imported coal. The Barsingsar Thermal Power Station consists of 2 units of 125 megawatt capacity each. These units were commissioned in December 2011 and January 2012. The power generated from this thermal power station is shared by the DISCOMs of the state of Rajasthan. The water requirement for this plant is supplied by the government of Rajasthan through the Indira Gandhi National Project Canal. All the power stations and mines of NLC India Limited are ISO certified for quality management system and environmental management system. Thermodynamic cycles. A thermal power plant works based on Rankine cycle and utilizes thermal energy for generating electrical power. The basic Rankine cycle consists of the 5 processes. They are pumping and heating, constant temperature heat addition, superheat addition, isotropic expansion, and constant temperature heat rejection. The basic Rankine cycle efficiency can be improved further by these ways: increasing the superheater steam temperature, increasing the superheater steam pressure, and increasing the condenser vacuum. However, in modern power plants, modified Rankine cycle is followed for the better cycle efficiency. 2 more processes is incorporated in basic Rankine cycle to improve cycle efficiency. They are reheating, regenerative feed water heating. Reheating is carried out just after the expansion of superheated steam in high pressure turbine. The exhaust steam of HP turbine is brought back to boiler and reheated in order to raise its temperature to the original value, and then it is allowed to expand in intermediate pressure turbine and low pressure turbine. Because of reheating, more work done can be obtained per unit mass of the working fluid. Regenerative feed water heating is nothing but raising the feed water temperature in low pressure heater and high pressure heater by the steam extraction from IP and LP turbines. Basics of thermal power generation. The chemical energy available in the fuel is converted into heat energy by combustion in the boiler. Then, the heat energy is transferred to the working fluid, that is, demineralized water, in order to produce high-pressure superheated steam. The feed water supplied to the boiler passes through economizer, drum, downcomber, and water wall tubes. Then it absorbs heat energy and is converted into wet steam. The steam and water is separated in the boiler drum. The saturated steam goes to the superheater and then expands in the HP turbine. The HP turbine exhaust is brought back to boiler for re-superheating and expands in IP and LP turbine, where the heat energy is converted into mechanical energy. The turbine is coupled to the generator, where the mechanical energy is converted into electrical power output. The steam expands in the turbine, loses its thermal energy, and is condensed in the condenser. The condensate so formed is recycled into the system. Any loss in condensate is made up by makeup water. Fuel handling system. The lignite from the mine is transferred to the power station by conveyor belts. A magnetic separator is provided at the receiving end to remove ferrous foreign materials. A stacker machine is used for stacking the lignite in the open storage yard. Reclaimers are used to reclaim the lignite from the stockyard. The stored lignite may vary in size, hence it is transported to the screener-cum-crusher house, where the lignite is crushed to 80 mm size by the roller crushers. Metal detectors have also been provided to remove non-ferrous foreign materials which are more than 30 kilograms. Then, the lignite is transported and stored in the boiler bunkers. Lignite handling system. Neyveli thermal power plants are pit-head power stations, that is, the power plants are located near the mines. The primary fuel for the Neyveli thermal power plants is lignite, which is low-grade coal with gross calorific value of 2700 kilocalories per kg. The lignite excavated at mines are transported to thermal power plant by belt conveyors. Then lignite is stored in the open stockyard or in closed bunkers. Water sprinkler is used to avoid spontaneous combustion of lignite. Stacker machines are used for stocking the lignite received from mines. Reclaimers are used to reclaim the lignite from the stockyard for sending the same to crusher house. In the crusher house, the lignite is crushed to 80 mm size by the roller crushers. Then, the crushed lignite is transported to boiler house and stored in boiler bunkers. Magnetic separators removes ferrous materials. Belt weighers have been provided to measure the quantity of lignite received. All lignite handling systems are monitored from the control room. Coal handling system. The primary fuel of NLC Tamil Nadu Power Limited is coal. A new coal jetty has been constructed by Tuticorin Port Trust, which will receive coal from ships. Mechanized shore unloaders have been provided to unload coal from ships and to load the same to jetty conveyors. Coal will be conveyed up to the crusher house through a double stream of conveyors. Provision has been kept to send coal either directly to boiler bunkers or to send coal to stockyard. coal stockyard has a storage capacity of meeting 30-day requirement of both the units. In coal storage yard, 2 numbers of stacker cum reclaimers have been provided along with the conveyors. Fuel oil handling system. Heavy fuel oil or light diesel oil is used as the secondary fuel for the boiler. Decanting facilities are available in power plants to transfer the oil from the tanker and lorries to fuel oil storage tanks. Fuel oil is used only during initial light-up of boiler, shutdown of boiler, poor quality of lignite, low load operation and special operation like safety valve floating, passivation, etc. Oil temperature at the tank is maintained around 80 degrees centigrade by flow coil heater. From the fuel oil storage tank, oil is pumped to boiler house by means of fuel oil pressurizing pumps. The oil temperature is raised near to fire point, that is 120 degrees centigrade, by means of secondary heater provided after pressurizing pumps. Then it is supplied to oil burner located in boilers. Boiler and its auxiliaries. Boiler, otherwise called as steam generator, supplies high-pressure superheated steam to turbine. Water and steam cycle. Boiler feed pump supplies feed water to boiler through high-pressure heaters with sufficient pressure and temperature. The feed water flow is regulated by pneumatically operated automatic control valves. Then the feed water goes to economizer, which improves the boiler efficiency by extracting heat from exit flue gas and thereby increases the feed water temperature. The water heated in economizer is sent to boiler drum, which is located at the top of the boiler structure. Then the water from drum flows through down combers to bottom header of furnace water valve. The furnace water valves are membrane type, which absorbs heat from the furnace. The steam water mixture formed in water valve rises up naturally and enters to drum through riser tubes. Steam and water is separated in drum, where the water goes down to downcomber again, and saturated steam goes to superheaters. Required safety valves have been provided in boilers to safeguard the vessel during abnormal pressure rise. The saturated steam passes through 3 stages of superheaters and picks up more heat from flue gas to become superheated steam. The superheated steam is carried by main steam line to the turbine. Steam temperature control. De-superheating spray system has been provided for maintaining required steam temperature. Cleaning devices. The superheater, reheater and economizer coils are cleaned by long retractable steam soot blower periodically. The furnace is cleaned by online water jet lancer periodically. Auxiliary steam system. Auxiliary steam system has been provided for meeting steam requirement of various auxiliaries of power plant. The steam is tapped from main steam line or cold reheat line. Then the temperature and pressure is reduced and supplied to the various auxiliaries. Firing system. Tangential suspension firing system is adopted in these boilers. The lignite stored in the boiler bunkers are transported to belt conveyor by plate belt feeder. The lignite quantity can be varied by adjusting variable frequency drive motors. The conveyor belt carries the lignite to resuction duct in which flue gas is sucked from the furnace in order to dry the lignite. Then the lignite is pulverized in the beater wheel mill and carried to the lignite burner by the centrifugal action of beater wheel. The combustion air taken from windbox is thoroughly mixed with the pulverized fuel and admitted into the furnace through lignite burners, and complete combustion takes place in the furnace. Draft system. Balanced draft system is adopted in the boiler. The forced draft fan of axial flow, variable blade pitch control type sucks air from atmosphere and supplies for combustion. The steam coil air preheater is placed at the outlet of FD fan to increase the air temperature during initial light up of boiler. The steam taken from auxiliary steam header will be used for heating the air passing through steam coil air preheater. The induced draft fan sucks hot flue gas from furnace through regenerative air preheater and electrostatic precipitator, then lets out the same to atmosphere through chimney. The induced draft fans are also axial flow variable blade pitch control type. Regenerative air preheater. In the bisector type regenerative air preheater, flue gas goes out from furnace through one half. Through the other half, air from forced draft fan comes into the furnace. The air preheater rotates at slow speed, that is 2 rpm, by means of an electric motor. The heat contained in hot flue gas is transferred to the incoming air, thereby increasing the air temperature, and the flue gas temperature is reduced. This helps to increase the boiler efficiency. Electrostatic precipitator. Electrostatic precipitator removes the fly ash from the flue gas so that the suspended particulate matters in stack outlet is maintained within acceptable level. Chimney. The dust-free flue gas is discharged to atmosphere by ID fan through chimney. The height of the chimney helps proper dispersion of flue gas into atmosphere, thereby reduces ground level concentration of pollutants. Circulating fluidized bed combustion. Circulating fluidized bed combustion. The firing system of these boilers differ from the pulverized fuel firing boiler. The lignite, which is less than 10 mm size, is fed into the combustor directly. Nearly 550 tons of bed material of size ranging from 0.2 mm to 1 mm size is already charged in the combustor. The primary air supplied through number of nozzles provided at the bottom of the combustor fluidizes the lignite along with bed material. Required secondary air is supplied to the combustor to ensure complete combustion. The hot bed material circulates internally in the combustor and dissipates heat to the surrounding water walls. Some portion of the fine bed material goes out of the combustor and returned back through recirculating cyclone. The bed material from the cyclone can also be diverted to bed heat exchangers, where the heat is transferred to part of reheater and superheater placed there. The hot flue gas goes out of the combustor, passes through the second pass, where it transfers heat to superheater, reheater and economizer. Then passes through air preheater, electrostatic precipitator and goes into the atmosphere through chimney. The fly ash collected in electrostatic precipitator is disposed of by dry ash collection system. The bottom ash is collected and cooled in ash coolers, which are placed at the bottom of the combustor, and then it is transported to bottom ash silo by conveyor belt for disposal. Advantages of circulating fluidized bed combustion. The combust temperature is maintained less than 860 degrees Celsius, hence nitrous oxide emission is minimized. Lime is added to the combustor for capturing sulfur oxide. Thus, sulfur oxide emission is also minimized. Hence, it is eco-friendly boiler. The circulating fluidized bed combustion boilers at TPS-2 expansion is of new technology. This is the first of its kind in India for 250 megawatt units. These boilers are more efficient and eco-friendly. Turbine and its auxiliaries. The turbine is 3 cylinders condensing, single reheat, regenerative, tandem compound reaction type. Turbine consists of casing and rotor. The blades assembled over the casing are called fixed blades, and the blades assembled on the rotor are called as the moving blades. One fixed blade wheel and one moving blade wheel is called as one stage. HP cylinder consists of 1 impulse and 22 reaction stages. IP cylinder consists of 17 reaction stages, and LP cylinder consists of 5 reaction stages. Boiler supplies superheated steam to HP turbine through main steam lines. After the work is done, the exhaust from HP turbine reaches to reheater arranged in boiler through cold reheat lines. The reheated steam is taken to IP turbine through hot reheat line. Then the steam expands in IP and LP turbines. The exhaust from the LP turbine passes through condenser where it is condensed. The condenser is surface type, single shell, rectangular, and 2 passes in construction. Sponge rubber ball type online tube cleaning system has been provided for condenser tube cleaning. The main condensate from condenser hot well is pumped to deaerator by means of condensate extraction pump. The ejector creates vacuum inside the condenser by sucking air and non-condensing gases from the condenser. The gland steam condenser condenses the turbine gland steam and the lack of steam from turbine valves. It is located after the main ejector. Then, the main condensate passes through low pressure heaters where the temperature is raised and then goes to deaerator. Deaerator removes dissolved gases in the feed water in order to avoid corrosion in boiler water tubes and drums. Boiler feed pump sucks water from deaerator and feeds to boiler through high pressure heaters. Regenerative feed water heating system. The low pressure and high pressure heaters are used to increase the feed water temperature by the extraction steam from LP, IP turbines and cold reheat line. Both heaters are vertical type. The drain condensate of LP heater is cascaded to hot well through a drain cooler and flash box. The drain condensate from HP heater is sent to a deaerator. Circulating water system. The circulating water flows through the condenser tubes and takes away the heat from exhaust steam of LP turbine, thereby condensing it. The water pumped from mines is stored in circulating water lake is used as cooling medium. Circulating water pump will pump the water to condenser through large size pipelines. This water removes heat from condenser and becomes hot and then goes to natural draft cooling tower for cooling. The cooled water from cooling tower basin will flow back to circulation water pump house by gravity through open channel. Then it will be pumped again to the condenser. The losses in the circulating water is made up directly from the circulating water lake. High pressure and low pressure turbines bypass system. Specially designed hydraulically operated valves have been provided for the main steam to bypass the high pressure and low pressure turbines. These valves will be kept in operation during initial startup of unit, tripping of turbo generators and house load operations. Turbine oil system. Turbine oil system consists of one main oil tank along with lube oil coolers, main oil pump, auxiliary oil pump, emergency oil pumps, jack oil pump, etc. It supplies oil to turbo generator bearings, lubrication, LP bypass system, turbine governing system, hydraulic turning gear and jacking oil turbo generator rotor. Auxiliary cooling water system. Auxiliary cooling water pump supplies demineralized water to various auxiliary equipments for cooling purpose. This is a closed cycle system where the warm water is cooled by circulating water in plate heat exchanger. Auxiliary cooling water is used in the following auxiliaries. In boiler zone, steam and water analysis sample coolers, lube oil coolers of ID fans, FD fans, air preheaters, pulverizer mills and afterburning grate shaft cooling. In air compressors, intercooler, aftercooler, jacket cooling of HP and LP cylinder. Turbine zone, lube oil cooler in condensate extraction pump, governing oil system, working oil cooler, mechanical seal cooler, seal box cooling in booster pump and main pump. In generator zone, hydrogen gas coolers. Air compressor system. Service air compressor supplies air with 8 kg per centimeter square pressure for cleaning the equipment, floors, etc. during maintenance work. Instrument air compressor supplies air through air dryers. The air is used for actuating all pneumatically operated control valves, control air dampers and pitch control mechanisms of ID fans and FD fans. Generator and its auxiliaries. Generator. Generator is a device which converts mechanical energy into electrical energy. It consists of a stationary armature stator and a rotating magnetic field, the rotor which is driven by a turbine. Whenever a rotating magnetic field cuts the stationary conductor, there induces an electromotive force which causes power flow. The power from the generator is connected to the grid through the generator transformer. The two main parts of generator are stator and rotor. The stator is a stationary part of a generator which consists of stator core, stator winding with hydrogen cooler and terminal bushings. The rotor is the rotating part of the generator which provides the magnetic field and rotates at 3000 rpm. It consists of rotor winding slots, ventilation ducts, retaining ring, cooling fan, slip rings, brush gear assembly and coupling. Generator auxiliary systems. Hydrogen cooling system. Hydrogen gas is used as a cooling medium in generator because of its less density, high heat transfer coefficient and high thermal conductivity. Seal oil system. In order to prevent the escape of hydrogen from the generator, there is oil in the shaft seal body with seal ring at both ends. The oil pressure is kept higher than the hydrogen pressure. Stator water cooling. The demineralized water flows through the hollow conductor in stator winding to cool the same. The cooling water must have an electrical conductivity less than 2.5 micro-mole per centimeter. Excitation system. The main function of the excitation system is to feed the DC voltage to the rotor windings to generate the magnetic field. It consists of excitation transformer, thyristor rectifier banks and regulator with operation control circuit. Power transformers. Transformer is a device that transfers electric energy with changed value of voltage and current. It can be classified based on application. Generator transformer is the high-capacity transformers connected between generator and high-voltage bus to evacuate the power at high voltage. Unit auxiliary transformer is a transformer fed from a generating unit to feed the auxiliary buses or loads of the same unit at reduced voltage. Station transformer is a transformer fed from high voltage grid to feed the common loads of the station. Switch yard. The generated power is distributed through switch yard and is regulated from switch yard control room. In switch yard, there are main buses which are common point, connecting number of incomers and feeders. Apart from main buses, there are transfer bus, bus coupler, current transformer, capacity voltage transformer, isolator, extra high voltage circuit breakers, earth switches, lightning arresters and wave traps that are located in switch yard. Water chemical treatment plant. Water chemical treatment plant. The borewell water is treated into DM water using ion exchange process. The suspended solid and coloring matters are removed in pressure sand filters. Then the cation filters remove cations like calcium, magnesium, sodium, potassium, etc. in the first stage and the escaped cations in second stage. The carbon dioxide formed during cation exchange is removed in degasser tar. The anion filter removes chloride, carbonate, sulfate, etc. in first stage and silica in second stage, and thus DM water is produced. The quality of DM water with pH value 6.8 to 7.2, silica less than 0.2 ppm and conductivity less than 0.5 micro-mole per centimeter is ensured before pumping to boiler house. Cation filters are regenerated with hydrochloric acid. Anion filters are regenerated with sodium hydroxide. The effluent formed during regeneration process is collected in effluent pit and pumped out after neutralization. Water chemical treatment plant supplies demineralized water for initial filling up of boilers and making up the water losses in thermal cycle. The borewell water passes through pressure sand filters, cation exchangers, degasser tar, anion exchangers for converting into demineralized water, and it is pumped into condensate storage tank from DM plant. Then the transfer pump supplies DM water to make up the system losses. pre-treatment plant and RODM plant.
In Thermal Power Station 2 expansion, stormwater from mines is treated in pre-treatment plant to produce clarified water and is made to pass through the main clarifier water. Then it passes through the gravity sand filter and softeners, which are used for circulating water makeup. The DM clarifier, which is pumped to the RO plant through the dual media filter, activated charcoal filter and cartridge filters to produce permeate water. Then the permeate water passes through mixed bed to produce DM water. In Thermal Power Station 2 expansion, instead of borewell water, stormwater from mine 2 is used for producing DM water, and reverse osmosis process is introduced before ion exchanges. The raw water is treated in an aerator for the removal of ion present in raw water. Then it is sent to pre-treatment plant to produce clarified water. The main clarifier water is used for circulating makeup water system. The other part of DM clarifier water is pumped to RO plant through dual media filters, activated carbon filters and micron cartridge filters. Then high pressure RO pump supplies the same RO modules arranged in two streams. The treated water from RO modules is stored in permeate water storage tank. Then DM plant supply pump supplies the permeate water to mix it bed to produce DM water with required quality and stored in DM water storage tank. Laboratory services. The laboratory attached to water chemical treatment plant analyzes and ensures the quality as per norms. It analyzes boiler water samples and circulating water samples, lignite proximate, fly ash and bottom ash, furnace oil, lube oil, transformer oil and hydrogen gas. Ash handling system. Wet ash disposal. The fly ash carried by the flue gas is collected in the electrostatic precipitator. It is mixed with low pressure water in the ash mixing vessel to form slurry. The slurry is moved to slurry pit by high pressure water jet. Then the slurry is pumped to the ash pond by ash slurry pumps. Dry ash collection. The ash transporter collects the fly ash from the electrostatic precipitator hopper. Then it is mixed with fluidizing air and transported to silos by transporting air, which is supplied by air compressors. From the silo, the dry ash is sent to the cement plant with the help of closed trucks. The coarse ash particles which fall down from the furnaces is known as bottom ash. It is collected in the slag bath which is placed at the bottom of the furnace. The slag conveyor discharges the same to the conveyor belt for loading them onto the open trucks for the disposal. The fine ash particles carried along with the flue gas is known as fly ash, which is collected by the electrostatic precipitator and mixed with low pressure water to form slurry. Then the slurry is pumped by the ash slurry pumps into the ash pond. At present, instead of wet ash collection, dry ash collection is adopted. In dry ash collection, the ash transporter receives fly ash from electrostatic precipitator hopper. Separate air compressors supplies air for transporting the ash to the silos. From the silo, it is sent to the cement plant by closed trucks. Controls and instrumentation. All the power station equipment like boiler, turbine, generator, lignite handling system, ash handling system and water system are controlled by state-of-the-art controls and instrumentation system.
The latest versions of distributed control systems are always implemented in NLC India Limited power stations to take advantages of the new developments.
C&I is brain and eyes for operations in our power stations.
NLC India Limited's contribution in renewable energy. Green Power Initiative of NLC India Limited includes wind power project.
51 megawatt wind farm at Karinir Kulam in Tirunelveli district. A 10 megawatt solar power plant has been established at Neyveli.
NLC India Limited's project under construction.
Neyveli New Thermal Plant 1000 megawatts. This power plant has been installed in the line of Thermal Power Plant 1, which has served its life. Proposed future projects.
Team aims to attain greater heights by 2020. By 2025, NLC India Limited would generate 19,331 megawatts power, which includes renewable energy sources of 4,000 megawatts solar power plant, 251 megawatt wind power, and its lignite and coal mining capacity would be 74.9 million tons per annum.
Wish you safe and successful completion of training.
NLC India, harnessing energy, spreading smiles.